Welcome back, guys. So today we're going to discuss, we're going to go a little deeper into exponential functions. And so today we're going to discuss geometric sequences. Okay, and so a geometric sequence is just a ratio of where you have a list of numbers where the ratio of consecutive terms is constant. Okay, and so you've seen in module 6 where we've had arithmetic sequences and we had a common difference. So for example, if we had, say, let's say we had the list 5, 10, 15, 20, and 25, right? We know that for every in between every set of consecutive terms, we have that we're adding 5. Okay, and so this was our common difference. Today, what we're going to discuss is a geometric sequence where we have in between every set of terms, for example, the list of terms that we have here, 5, 10, 20, 40, and 80, that we can find a common ratio represented by R. And if you remember back to how we find our common ratio, we take the ratio of our successive terms. So we would have 10 over 5, which is 2. We have 20 over 10, which also gives us 2. 40 over 20, which gives us 2. And 80 over 40, which gives us 2. So in this case, our common ratio, or R, would be 2. Okay, and so one of the things that I wanted to mention was the types or representations of ways that we can see geometric sequences presented to us. All right, we can see them as a list where we just have like a list as such, or we can see them in a table where here our n represents our term. So this is the first term, second term, third term, fourth term, fifth term. And then we have the actual term 5, 10, 20, 40, and 80. Or we could see them in a graph where we're given coordinate pairs where we have 1, 5, which represents the x represents the number of the term, and the y represents the term itself. And if you notice, whenever we are given a graph of a geometric sequence, we do not connect the dots because we are only dealing with discrete numbers. We never have a zero term, or we can never take the terms in between these 2 points, for example, and put those in our geometric sequence because they may not give us the same common ratio. Okay, so let's take a look at a specific example of a geometric sequence. Makers of Japanese swords in the 1400s repeatedly folded and hammered the metal to form layers. The folding process increased the strength of the sword. The table shows how the number of layers depends on the number of folds. Write a recursive rule and an explicit rule for the geometric sequence represented by the table. Okay, so in this example, we have an actual table. We're given our geometric sequence in a table. So we know that these are the term numbers, and this is our actual sequence. Okay, so in order to write a recursive rule, and recursive just means one after the other, how we figure out how to get from one term to the next. All right, so to write a recursive rule, we're going to start with the first term. So we're going to write f of 1 is 2. And then we're going to say f of 2 is now 4. But we can write f of 2 or 4 as 2 times 2. Okay, f of 3 is 8, which we can also write as 2 times 4. F of 4 is 16, which we can write as 8. Let's write that as 2 times 8. Okay, so let's write this as 2 times 8. And then f of 5 is 32, which is 2 times 16. Okay, and if you notice, as we progress in term number, so from one term to the next, we are simply taking our first term, which is 2, and it's constant in each term, and we're multiplying it by the previous term. So here we have 2 times our previous term. So this is actually 2 times f of 1. Here, this is 2 times f of 2. And so forth. 2 times f of 3. And 2 times f of 4. All right, so if we wanted to write a recursive rule, we're always going to start with our first term, f of 1 equal to 2. And then we're going to, we want to write how we get to, express how we get to each consecutive term, right? So our pattern is that we take 2, so f of n is going to be 2 times the previous term, or f of n minus 1, where in this case n is greater than or equal to 2, because we've already stated our first term. Okay, so this is the recursive. All right, and so now we want to find an explicit function for this. So if we notice, we can also write our, we can write this table another way. So we have n, f of n, and so when n is 1, f of n is 2. When it's 2, it's 4. 3 is 8. 4 is 16, and 5 is 32. Okay, and so what we want to do is we want to express these. This is simply 2 to the first. This is 2 squared. This is 2 cubed. 2 to the 4th power, and 32 is 2 to the 2 to the 5th power. Okay, and so if you notice, we can write all of these as powers of 2. So for our explicit formula, we have that f of n is actually equal to 2 raised to the n power, where n represents the number of the term. Okay, and so that's our explicit formula for this situation. All right, and so just a few general rules. We have that our recursive rule is given f of 1. We can write f of n equal to f of the previous term, f of n minus 1 times the common ratio for n greater than or equal to 2. And the explicit rule is f of n equals f of 1 times the common ratio raised to the n minus 1 power. Okay, and also what I want to point out is that once you move into algebra 2, you'll start seeing you'll no longer use this function notation for recursive and explicit rule. You'll start seeing this this subscript notation, right, where we have a of n represents some sequence, and so a of n is some term where n is the term number and n minus 1 is the previous term. Right, so in each of these, the subscript represents the term number, and this, so a of 1 would be our first, the first term in our sequence. All right, so let's take a look at an example where they give us certain terms in the sequence, and we must find an explicit function from that. So we have the shutter speed settings on a camera form a geometric sequence where a of n is the shutter speed in seconds and n is the setting number. Okay, so just from that, let's set up our chart. So we have that, we have n and we have a subscript n. Okay, and so we have that the 5th setting on the camera is a 60th of a second, and the 7th setting on the camera is a 15th of a second. Okay, and we want to write an explicit rule for this sequence using subscript notation. All right, so we know that the 5th setting is, so this would be term 5, is 1 over 60. And we know that the 7th setting is 1 over 15. All right, and so what we want to do is, remember, we want to grab our explicit function using subscript notation. So we have a of n is equal to the first term times the common ratio raised to the n minus 1 power. Okay, and so what we want to remember here is that we don't know our first term and we don't know our second, third, fourth. We do know our fifth, we don't know our sixth, and we know our seventh. But we know how to get from term to term. To get from term to term, we just take the previous term and multiply it by our common ratio. Right? So let's set up some expressions to show that. So to get a to the sixth, we can take a to the fifth and multiply it by r. To get a to the seventh, or our seventh term, we take our previous term, which is a sixth term, and multiply it by r. Right? And so if you notice, we have a to the sixth written in terms of its previous term and the common ratio, and we know what the fifth term. So let's use that in our second expression. So we're going to substitute. Let me just highlight what we're going to substitute. So we're going to substitute this expression into a sub 7. Okay, so we're going to take a sub 7, and now for a to the 6, we're going to substitute in a sub 5 times r, and we're going to bring back this, remember to bring back that extra r. Okay, and so now we have an equation of two knowns and one unknown, and we can solve for this unknown. All right, so let's do that. All right, a sub 7 is the seventh term, so we know that's 1 over 15. And a to the fifth is 1 over 60 times r squared. And so we want to multiply both sides by its reciprocal of 60. And same thing on the left-hand side. And so we get that r squared is 4. And so r is the square root of 4, because we must square root both sides, is 2. So we know that our common ratio is 2. Okay? And now we can use that in our formula. A sub n equals a1 times r to the n minus 1 to find what our first term is and write our explicit function. Okay? So we're going to plug in. We don't know a sub 1. We do know r, which is 2. And then to find what a1 is, we're going to choose one of our points. So I'm going to choose a sub 5, which is 1 over 60. And so we know that n is 5 minus 1. Okay, so we chose the point 5, 1 over 60 as our point to plug in. Okay, and so now we're just going to solve for a1. So a1 times, this is now 2 to the 4th, equals 1 over 60. And so we get 16a1 times 1 over 60. And we're going to multiply by the reciprocal. So this is 16 times 1 over 16, a1. And then 1 over 16 times 1 over 60. So this cancels. And so we get a1 is 1 over 960. Okay, and so now we have all the values we need to write our explicit formula. So our explicit formula for this geometric sequence is going to be a to the n. The first term is 1 over 960 times our common ratio is 2, n to the 1. And that will give you the shutter speed at any rate in that we plug in. Okay. All right. Now let's look at the graph we have where our situation is a graph. So the graph shows the heights to which a ball bounces after it's dropped. Write an explicit rule for the sequence. All right, so again, we want to grab our explicit function for our explicit rule, so which is a1 times r to the n minus 1. And so from this graph, we know that our list is 100, 80, 64, and 51.2. All right, so we know our first term. Our first term is 100 because 1 corresponds to 100. So we can fill that in. That's 100. But now we must find r. And in order to do that, we just take the ratio of our successive terms. So we have 80 over 100, 64 over 80, and 51 over 2. And remember, in geometric sequences, our common ratio is constant throughout. So all of these ratios should give you the same common ratio, which would be 0.8. Okay, and so our r in this case is 0.8. So we'll fill that in, raised to the n minus 1. And then we can find, so this explicit function represents the information that's given in our graph, which shows the height to which a ball bounces after it's dropped. Okay, and that is the end of today's lesson.